Hello and welcome to our third lecture. Today's lecture covers 2.4 and 2.5. There are a good number of problems that are on the easier side, and I was going to do examples about them, but MyOpenMath has a good number of videos that correspond to some of the easier problems, so I'd like to concentrate my attention today on the more difficult word problems. Okay, so the first problem I'd like to start with is number 58 from page 81, angle of elevation of the sun. So when it comes to angles of elevation and depression, think about your eyes as the horizon. Now, if you elevate your eyes from the horizon, that is, you look up, you will have your angle of elevation. But if you are looking at the horizon and then you look down, that would be angle of depression. So always start off with the horizontal as the horizon, and then from that initial point of horizon, look up, angle of elevation. So in this problem, it says the length of the shadow of a flagpole, 55.2 feet tall, is 27.65 feet. Notice that for both numbers, we have 4 significant digits. Find the angle of elevation of the sun to the nearest hundredth of a degree. So I will start by drawing a diagram, which is what you will need to do for every single problem that does not have a diagram provided. You need to draw a diagram and then mark it up appropriately. So let me go ahead and do that. So here is my flagpole. It's a reasonable assumption that the flagpole would be at a right angle with the ground. For all of these triangles, in Chapter 2, we need to have right triangles. Later, we'll learn how to solve problems when the triangles are not right triangles, but in Chapter 2, you will always end up with a right triangle, okay? So here is the right angle. Now, the angle of elevation to the sun is from the flagpole going up to the sun. So if the flagpole had a horizon, then from the horizon up to the sun, here's the sun, that would be your angle of elevation from the horizon at the flagpole to the sun. Now, since this horizon line is parallel to the ground line, then this angle right here is congruent to this angle right here, because these would be corresponding angles. That's why those parallel lines cut by a transversal concepts earlier in Chapter 1 were so important. So what we need to do is figure out what this angle is. I'll call it theta. So I need to label my sides. I have a flagpole that's 55.20 feet, and then I have a shadow that is 27.65 feet. So in relationship to this angle theta, this side right here would be the adjacent side, and then this side right here would be the opposite side. So here is adjacent, and here is opposite. So which trig function uses adjacent and opposite, or opposite and adjacent? Tangent, TOA. So what we want to do is set up the equation. Tangent theta is equal to opposite over adjacent. So far there are 2 pieces of required work. 1, a diagram that's fully labeled, including with a right angle and your variable and any lengths that are given. And 2, a tangent or a sine or a cosine equation that is going to show the ratio. Okay, so at this point now we are going to do tangent inverse on the calculator. So to find theta, we want to make sure that the degree mode is on in the calculator, not radian mode. Theta is equal to the tan inverse of 55.20 over 27.65. We use tan inverse or sine inverse or cosine inverse anytime we know the full ratio, but we are missing the angle measurement. So now we type this into the calculator. make sure my mode is in degrees. Yep. Then I do tan inverse, 55.2 divided by 27.65, close my parentheses, and I end up with theta is approximately, and I have 4 significant digits for both of these numbers, so that means I'm going to use 4 significant digits here. So this would end up being 63.93 degrees. Okay, so that would be the first one. And now for the second problem from 2.4, let me erase the board and get that all set up. Okay, so I'm going to do number 56 from page 80. And this problem will help you with both number 47, although that does have a solution in the back. Remember, anytime you have a green highlighted number in the textbook, it means that there's a solution in the back of the book and you want to study that. But this will also help you with number 14 from My Open Math for homework 3. Okay, so what we have here is we have a small building and we have a tall building. And the angle of elevation from the top of the small building, so here we are at the top of the small building, and in order to have an angle of elevation, that means we need to have a horizon line, and then we're going from the horizon up to the top. Okay, so this angle of elevation is 46 degrees, 40 minutes. And the angle of depression to the bottom of this other building, so here's the horizon line again. Angle of depression would be the angle going down. So I'm going down from the top of the small building to the base of the tall building, and this angle right here is 14 degrees, 10 minutes. Now, it's safe to assume this is not the Leaning Tower of Pisa, so we have a perpendicular between the ground and the building, which would make this angle, this horizon line, hit this tall building at a right angle. We know that the shorter building is 28.0 meters high. So this right here, 28.0 meters, would correspond to this length right here. From this point to this point, this line segment is going to be 28.0 meters as well. Here we have this rectangle. Now we're going to find the height of the taller building. So we know this much. What we need to do is find this piece right here. So I will call this piece H. H will not be the entire height. The height of the tall building is going to be H plus 28.0 meters. So when we add these two pieces together. Now, we cannot use right triangle trig on this top triangle until we have at least one side measurement. Right now we have no side measurements. We only have an angle. But what we can do is by looking down here at this lower right triangle, remember this would also be a right triangle, we can figure out what this length is right here by using tangent. We can figure out x, and then once we know x, we can use tangent again for this upper triangle. So it's a two-step process. So first, we're going to use tangent on the lower triangle. So the tangent of 14 degrees 10 minutes is equal to opposite over adjacent. Okay? Now, we can set up another tangent ratio then for the top triangle. The tangent of 46 degrees, 40 minutes, is equal to opposite over adjacent. So opposite over adjacent. So what is H? H, if you cross multiply, is x times the tangent of 46 degrees, 40 minutes. Now, I left this as an x. I didn't put it in as a number yet. And the reason I didn't put it in as a number yet is because I don't want to have a rounding error. So when I set this up, I know what x is. If I solve for x here, I have that x is equal to 28 over the tangent of 14 degrees, 10 minutes. So what I wanted to do is get this situation set up so that h is already solved for, and then x is right here, and all I have to do is now plug in this value for x. So I'm going to take this value right here, I'll type it into the calculator now, and then I'll multiply it by tangent of 4640. So you can change everything from minutes, from DMS form to decimals, but you could also just in-line do your conversion. So what I mean by that is when you want to type tangent 14 degrees 10 minutes, rather than go through the process of converting this to decimal form and then taking the tangent, you can type in something. Let me lower this a little bit. You can type in tan 14 plus 10 over 60, and that would convert from DMS form to decimal form at the same time as taking the tangent. So to get x, though, we want to take 28 and divide 28 by the tangent of 14 plus 10 over 60. Make sure you then close your parentheses, and then you would multiply by tangent 46 degrees, 40 minutes. Okay, and when I do that, I get that h is approximately 117.5749 ... What would we need to round to in a problem like this? We would have 3 significant digits. So the reason we have 3 significant digits, we see that we have 3 significant digits here with 28.0. We also have 3 significant digits given to us by the degrees having 2 digits, and then the minutes having 1 significant digit. So we're going to round this to 118 meters, and then when we add 118 and 28 together, we get 146, right? So 146 meters is your total height. That is h plus 28. So that problem should help you with the MyOpen Math problem that has the 2 different triangles, as well as problem 47 from your book. Okay, so now what I want to do is I want to move on to 2.5, which is the harder section, and that has to do with navigation. And first we need to talk about the 2 different ways that bearing is indicated. Okay, so there are 2 different ways that we can indicate bearing. One is through a single angle that's given with no north or south or west or anything like that. And we would then always take the bearing clockwise from the north. Okay, so bearing method 1 says that you have a north arrow of a compass, and then going clockwise from that north arrow, you can get to any angle that you want. And bearing is the direction a boat or an airplane or anything is heading, okay? So if you want your boat to be heading in this direction right here, and it turns out that the angle from here to here, this is clockwise, which is the opposite of when we're graphing angles in standard position. Normally when we're graphing angles in trig, we start on the x-axis and we go counterclockwise, but in bearing you actually start at the north, which would be the y-axis basically, and then you go clockwise. And so let's say this is a 120 degree angle right here, then we would say that the bearing of this ship is 120 degrees. So that is one way of doing bearing. The second method of doing bearing involves using a north-south line and then going towards the east or going towards the west. So let's look at the same trajectory with bearing method 2. Bearing method 2 always presumes that we have a north-south line. And then from the north or from the south, we then either head east or west. So because this trajectory here is closer to the south than to the north, we would actually do this bearing method in relationship to the south. So here we have, again, the same trajectory. We want to ask ourselves, okay, if this is a 120-degree angle here, then the angle here would have to be 60 degrees, right? So this is the same trajectory here as we have up here, this red arrow and this red arrow. It's 120 degrees from the north, but it's only 60 degrees from the south. So we're going to say we're going to start at the south, and then we're going to head 60 degrees towards the east, right? Since this direction here is east, we would say south 60 degrees east, or we would say 60 degrees east of south. And that's a different way of expressing bearing. So how do you know which one it is? Well, if you don't see any south or east or west or north labels on either side of the angle, if you just see a plain old number, then you know you're dealing with method 1, and it's clockwise from the north. If you do see these north, south, east, west labels on either side of the number, then you know you're dealing with bearing method 2. Okay, so now I want to look at question number 16. This can be a little confusing from my open math. We have to differentiate between the direction angle and the bearing of two vectors. So let's look at the blue vector for instance. The direction angle is what we have been using so far. Okay, so the direction angle would be, suppose you were to start at the positive x-axis, and then you take from the positive x-axis, you draw your angle counterclockwise to the terminal side. That is your direction angle. Since 180 degrees plus 32 degrees, so we have 180, plus 32 is 212, then the direction angle of the blue vector is going to be 212. And there it is. Now that's going to be different than the bearing of the blue vector. The bearing of the blue vector means that we start at due north. So here's due north. And then we go clockwise. So bearing has us start at due north and go clockwise. So here we have 180 degrees. But then from this negative y, or this south line, to the blue vector, we have 58 degrees, right? So we have a 58 degree angle here, and then we need to add that 58 degree angle to the semicircle, to the 180 degree angle. And if you add those two together, then you're looking at 238 degrees for your bearing. So we're not dealing with method 2. We're just learning the difference between the direction angle we have been dealing with prior to this lecture and bearing method 1. Okay, so the next problem I'd like to work through is page 87, number 26. And in this problem, it says that we have a diagram already given to us. So let me go ahead and put that diagram up on the board. So here's our diagram. We have radio direction finders are set up at points A and B. They are 2.50 miles apart. Notice the 3 significant digits. This is an east-west line, which is important because if this is an east-west line, then relationship to the north lines would be that we have right angles here and we have a right angle here. From A, it is found that the bearing of a signal from a radio transmitter is 36 degrees 20 minutes east of north. So this is bearing method 2. And from B, the bearing method, the bearing to the transmitter, this is the transmitter right here, I'll call the transmitter T, is that it's 53 degrees 40 minutes west of north. So these also have 3 significant digits. We need to find the distance of the transmitter from B. So here's where we can label with a chosen variable. You can choose what you want your variable to be. Now, this diagram is provided for you, but it's an incomplete diagram. So you do need to make sure that you complete the diagram. Remember, we want a fully labeled diagram. The diagram should include the right angle, and it should include the variable that you're solving for. So I've already added the variable of my choice, D for distance, to transmitter B. But I also need to figure out where the right angle is. Now, of course, I do have right angles here and here. And what that's going to tell me is that this angle right here would have to be the complement of 36 degrees 20 minutes. And the complement of that is 53 degrees 40 minutes. And then this angle right here must be the complement of 53 degrees 40 minutes, which is, of course, 36 degrees 20 minutes. So they set this problem up so that these 2 angles were complementary angles. If these 2 angles add up to 90, that means that this angle here is going to be your right angle. Don't ever assume where your right angle is, though. Use your knowledge of parallel lines cut by transversals and the triangle angle sum theorem to figure out exactly where your right angle is. Okay, so now that we have our right triangle, we can use either one of these angles here, it doesn't matter, and then this side length. So, for instance, if I were to choose to use angle B, well, this angle B is a little vague, right? There are multiple angles at B. But if I were to use this 36 degree 20 minute angle at B, then this side right here would be adjacent. And then, sorry, that's the hypotenuse. So this is always going to be the hypotenuse. It's opposite the right angle. This one is the adjacent side. So if you choose to go from this side, you would have the cosine of 36 degrees 20 minutes equal to the adjacent side, D, divided by the hypotenuse. Alternatively, you could have started at this angle over here. And in that case, D is not adjacent, but opposite. So D is adjacent to the point if you're going from point B. But it's opposite if you're going from point A. So that in that case, we would have the sine of 53 degrees 40 minutes equal to the opposite over the hypotenuse. We should not be surprised that both of these equal D over 2.50, right? Because cosine and sine are cofunctions, and 36 degrees 20 minutes and 53 degrees 40 minutes are complementary angles. That goes back to the cofunction relationship. So you can use either one of these. You just cross multiply to get D. You either multiply 2.5 by cosine of 3620 or 2.5 times sine of 5340. And either way, we're going to round to 3 significant digits. So we're going to have 2.01 miles as our final answer there. Okay, so after this, next I'm going to do number 28. Now, problem number 28 does not give us a diagram. The ones without diagrams tend to be the trickiest. Sometimes you can know all the trig in the world, but if you have a bad diagram, it can throw you off. I actually did that a couple of years ago in a lecture. I had misread one part of the problem that caused my diagram to be off, and I could not get the answer right. Unfortunately, one of the students in the class figured out my error, and he came up to me after class and pointed out why my diagram was incorrect, and I was able to then publish a correct diagram online to the students. But the good thing about this video is I can correct it right here for you. So hopefully I will not have a problem, and we will get this diagram right the first time. So let's read through number 28. If you have not had a chance to practice diagram drawing, let me recommend right now that you pause the video and go try to draw a good diagram for page 87, number 28, before you see me draw it, okay? And then after you've tried it, then replay the video. So, number 28, the bearing from A to C is 64 degrees west of north. Okay, so I have from A to C. I have no idea the length of the distance between A and C. It's kind of a shot in the dark. Sometimes you may even want to have a rough draft diagram and then a final draft diagram once you get a better idea of what you're doing, okay? I'm just going to start with A somewhere on the board. If you have a blank sheet of paper, do it in the middle if that helps. And now I'm going to go from A to C on a bearing of 64 degrees north of west. So west of north. So what I'm going to do is I'm going to start by drawing, I would recommend either a light pencil or a different color. I'm going to be drawing a north line from A. And now I need to go in the west direction 64 degrees. So I'm going to come out this way. 64 degrees. Just estimate. And so from A to C, which again I have no clue how far apart they're supposed to be, but at least this part is accurate so far. Then we continue. The bearing from A to B, oh, this is going to be fun, is 82 degrees west of south. Okay, so now I need to start at A, and I need to draw a south line. And then from that south line, 82 degrees west of south will be almost 90 degrees, so it's going to be like this. So here is 82 degrees west of south, and that would be the bearing from A to B. Now, these angles are correct coming from here, but I don't know if C is supposed to be further away or B is supposed to be further away, but I may find that out by the next clue. So I can always erase these and make either one of these longer or shorter depending on what happens next. So next we read the bearing from B to C. Okay, now we're going from B to C is 26 degrees east of north. What that means is I need B to be a little further out. So I'm going to go ahead and erase this here. This is where I find out that I need to make B a little longer. So using pencil is a great thing. Pencil in math in general is a great idea. Okay, so also whiteboard markers. Okay, from B, I'm going to have a north line. Here's my north line. And from B to C, I have to go 26 degrees east of north. So now I have a line going up to C, and that is going to be 26 degrees east of north. Wow, okay. So we haven't even got to label yet the distances at all. But let's just make some observations before I add any distances. First of all, notice that the red lines are parallel because they are north-south lines. We can figure out what this angle is right here, right? From north to south, that's 180 degrees. So if you take 180 degrees and you subtract from it 82 and you subtract 64, you should end up with a 34-degree angle, right? So that means I have a 34-degree angle. Okay, now where it gets a little trickier is trying to figure out what this angle is right here. This is where it gets a lot trickier. What I would do is take your south line. You haven't needed to draw the south line yet from B, but by doing so, I'm going to extend this parallel line. Okay? And next, let's see, do I have another color? Yes, I do. This angle right here, we would really love to know this angle right here, because if we knew this green angle right here, we could easily find out this angle in the same way that we found out this 34-degree angle, right? All we had to do was subtract 64 and 82 from 180. So how do we figure out what this angle is right here? Alternate interior angles. Okay, remember that alternate interior angles are congruent. So we have two parallel lines cut by a transversal. Here's your transversal. So this angle right here is alternate interior angles with this angle right here. That was the big tricky part there. Okay, if those are alternate interior angles, they are congruent, which would make this green angle down here 34 plus 64, or a 98-degree angle. So that makes your diagram a little cluttered. So if you had to then erase this green, we would still know that that's 98 degrees. So I'm going to go ahead and erase this clutter here. Sometimes it's worthwhile to draw sketches off to the side and mark them up as needed. So now I'm going to take 180 and subtract 98 and subtract 26, and I end up with a 56-degree angle. Never jump to conclusions. You do need to go through the process of figuring out what all these angles are using sound geometry. One of the things that math will teach you is what's called academic skepticism. Don't leap to a conclusion without knowing why that is true. Okay? Always ask yourself, how do I know that's true? You might have drawn this diagram and said, oh, there's the right angle. And you might have concluded that correctly without any sound reasoning. That is, you came to the right conclusion, but for the wrong reasons. Guessing is a wrong reason. The correct reason for why this is a right angle is by after we do all the work of figuring out that this is 34 degrees, and then this is 56 degrees, by observing that we have complementary angles here in our triangle, by the triangle angle sum theorem, then we know that angle must be a 90-degree angle. So we have finally found our 90-degree angle. Next, let's continue reading. A plane flying at 350 miles per hour takes 1.8 hours to go from A to B. Okay, if a plane is flying for 1.8 hours at a rate of 350 miles per hour, we simply multiply 1.8 times 350 and get 630 miles. So we're going to figure out that the length of this is 630 miles using dirt, right? Distance is equal to rate times time. Distance is equal to rate times time. You should have a certain intuition from real life about that anyway. This is 630 miles. Find the distance from B to C. So from B to C, we can pick any variable we want. I'm going to go ahead and call this side little a because little a is opposite angle A. You could call it D for the distance between B and C. It doesn't matter. It's your diagram. You label it with your variable of choice. But don't dive into writing any trig equations without first having a fully labeled diagram. Okay, so I can choose to use the 56-degree angle or the 34-degree angle. It doesn't matter. I'll just go ahead and pick the 34-degree angle. It's an arbitrary choice. The sine of 34 degrees is equal to opposite over hypotenuse. So then A is equal to 630 times the sine of 34. And here I am going to be looking at two significant digits. So I'm going to make sure that I round appropriately then. I've got 630 times the sine of 34, and that is going to give me 352.29. But 352 is three significant digits, so I need to pull that back to about 350 miles for two significant digits. Okay, so that was very challenging. So if you got through that diagram, you're on your way to success. Okay, so next let's take a look at question number 17 from my open math. From A to B, a private plane flies 2 hours at 110 miles per hour. That's a little easier to compute, right? That's 220 miles. On a bearing of 43 degrees. It turns at point B and continues another 1.9 hours at the same speed, but on a bearing of 133 degrees. So what I need to do is I need to start my diagram. Let's start down here. Here is going to be point A. Now I'm going to go on a bearing of 43 degrees. So let me get my bearing from the north. Here's north. And now my flight I'll make in blue, and this is going to be 43 degrees. That's close to 45, so I'll have it go like this. Okay, that's supposed to be a straight path. And I will label the angle here 43 degrees. Again, you can pause the video and try to set up this diagram on your own. So that gives me a point B now, and that point B is located right here. Next, from point B, I'm going to be traveling next on a bearing of 133. So let me get another north arrow. The north arrow is going to go right through B. That's north. And 133 degrees is going to be from the north, go down here, and we're heading out this way. I don't know how long to draw that yet, and I can't erase this, so I'm going to err on the side of going short. So here is 133 degrees. And that gives me point C. Okay, so actually I do know that it's going to be, since it's 1.9 hours versus 2 hours, these are going to be close to the same length, with this one a little shorter. Here's point C. Alright, now for the lengths of the sides, I don't want to clutter this too much, so let me just kind of draw with black some arrows here. This side right here is going to be 2 hours times 110, so that's 220. And then this side right here is going to be 1.9 hours times 110. And that's going to be 209. So, we need to look at these angles and how these angles will give us this angle right here. If we were to draw, let me do this in light blue, a south line right here. This south line is going to be parallel to this north line, which would make this angle right here a 43-degree angle because of alternate interior angles. And then this angle right here has to form a linear pair with 133. So that is going to have to be a 47-degree angle to add up to 180 degrees. So now you can see that 43 degrees and 47 degrees, that's a 90-degree angle. And I suspected as much, but I wanted to prove that it was. I used light colors so that I can kind of ignore those. I'm going to tune that out. I'm just going to put a nice big box here to represent the right angle. So now I know I have a right triangle. In all of these problems, if you don't end up with a right triangle, you can't do them according to Chapter 2 methods. That would be SOHCAHTOA. Okay, so now we want to know at the end of this time, how far is the plane from its starting point? So let's get this side from A to C. From A to C, this is, I'm going to label this side little b because it is opposite angle B. And C is where the plane is now, and A is going to be the starting point, and this would be a simple Pythagorean theorem problem. So if we use Pythagorean theorem, then B is going to equal the square root of 209 squared plus 220 squared. Here we're not dealing with significant digits. That's more of a book thing. We're dealing with rounding. So we would round to 3 decimal places. Okay, so let me type that into the calculator. 209 squared plus 220 squared, and then I take the square root of that. And that is going to be approximately 303.449. And make sure that seems reasonable for this picture. Yes, 303 miles seems reasonable. I can't click on this button until I get rid of my writing mode, until I get out of draw mode. We'll find out if this is 303.449. Now this is the harder question. On what bearing from due north is the plane from its original location? Oi. So what that is saying is we need to figure out the angle from this north line to B. So let's pick a color for that. We will make that, let's do a bright green. So from here to here, I'm going to call that theta. So this is going to be theta. To figure out that angle right there, we need to figure out what little angle A is, what angle A is. If you're looking at the triangle, then angle A, also known as angle BAC, is going to be part of theta. And we could do that using tangent so that we don't have to use the rounded side. So I'm going to call this one right here, that's on the inside, I'll just go ahead and call this little one right here alpha, because that reminds me of A. So that means that the tangent of alpha is equal to opposite over adjacent. And then to get alpha, we just need to use the tangent inverse. So alpha is then going to be tan inverse of 209 over 220. Okay, so moment of truth here. Tan inverse of 209 divided by 220 is approximately 45.531 degrees. And I'm adding that then to 43 to find out what theta is. So then this is approximately 88.531. And now I'm going to have to erase this to figure this out. So this is 88.531, and this is 303.449. Those are slightly different. Okay, let me see if I can figure out why. Okay, so I'm troubleshooting here. I've redone the diagram here. I'm certain of 220 and 209. I am certain that I came to the correct conclusion about this being a right angle. And now when I do this problem, I end up with little b is equal to the square root of 220 squared plus 209 squared, just as I did before. And when I type that in the calculator, that is 303.449. So either I got it right before and my memory was bad, or I did some sort of typo. But that is the correct answer, and that's how you get to it. Okay, we can flip back here and even see the 303.44. They didn't round, but you need to round because they will evaluate your answer based off the rounding. Okay, and then the other issue was the 86 degrees. So now let's go back to my diagram again. So I'm getting the correct answers here on the whiteboard. I don't know what I did differently on the computer. I can't rewind and go back. Maybe you caught my mistake. Maybe I wrote down one of these sides as a different number, but look right here, I have the alpha. Tangent of alpha is opposite over adjacent, so alpha is tan inverse of 209 over 220. That's 43.531, which means that this entire angle going from the north down to this line right here is 86.531 degrees. That would be the bearing. 86.531 degrees. And if we flip back over here to my open math, it matches this number right here. So while I did get some sort of error when I was doing it here, the technique and the procedure I was showing you was absolutely correct. And I would say this, that in math, it's very common to make mistakes. What you need to learn are your troubleshooting skills, to go back, tinker with it, see if you can replicate what you did, to see if you made an error, and persevere. And in my case, I had to. I didn't have a choice because I'm the instructor, right? So I got to redo it. In your case, your grade depends on it. So one of my life mottos is, I can because I must. It's simple, but that's what's getting me through a lot of days. Okay, so that wraps up our lecture today. Hopefully that answered a lot of your questions, and that will help you as you work through these more difficult word problems. And please let me know if there's anything I can do to help you. Have a great day.